It's everywhere, magnetism. It's in your fridge magnets, in technology. But believe it or not, it holds one of the deepest, most counterintuitive mysteries in all of physics. Forget the simple attraction you learned about. What if I told you its fundamental nature completely defies classical explanation, that it drags us kicking and screaming into the quantum realm?
That's exactly right. This deep dive is really about understanding why magnetism needs quantum mechanics. It just doesn't work otherwise. We'll explore how incredibly complex and, frankly, fascinating its behaviors are. We're going way beyond simple north and south poles here. It's why physicists are, well, obsessed with it, because understanding it could unlock truly exotic states of matter, things that could power future tech, maybe even fault-tolerant quantum computers or totally new electronics.
So our mission for you today is to unpack this fascinating world of quantum magnetism. We'll go from its really puzzling origins, the fact that classical physics fails, all the way to the cutting-edge search for entirely new states of matter. We'll dig into the core principles, the foundational ideas, and also the intricate experiments trying to unravel these secrets. And everything we discuss is drawn from a pretty comprehensive dive into the latest research and the key texts in this field. Okay, let's start unpacking this. You probably think you have a handle on magnetism. Magnetic fields, how compasses work, all that. But here's the twist. There's something called the Bohr-Van Leeuwen theorem in classical physics. It basically proves mathematically that a system of classical charges just bouncing around in thermal equilibrium can exhibit no net magnetization. Zero.
It's almost unbelievable, isn't it? But it's true. Classical physics literally cannot explain even a basic lodestone, a simple permanent magnet. It shouldn't exist according to those rules.
So classical physics completely drops the ball.
Completely. And this fundamental failure forces us, really compels us, to dive into quantum mechanics. The real origin of magnetism isn't about charges moving in circles classically. It lies in the electron's intrinsic spin angular momentum. And crucially, this isn't like a tiny ball spinning. It's a purely quantum mechanical property. It has no real classical counterpart.
Like it just has spin.
It just has it intrinsically. And this spin gives the electron a tiny magnetic dipole moment. Think of it as a tiny quantum compass needle. And it's the collective behavior of billions upon billions of these tiny quantum moments that creates all the rich magnetic phases we actually see in materials.
Okay, so quantum mechanics gives us the ingredients, these electron spins, these tiny magnets. But how do they actually talk to each other? How do they decide to line up or oppose each other? What's the driving force?
Right. The primary force dictating how these spins align or anti-align is called the exchange interaction. And what's really fascinating here, and maybe a bit confusing at first, is that it's not a new fundamental force. It's not like gravity or the standard electromagnetic force.
Not a new force. So what is it then?
It's an effective interaction. It kind of emerges from two core quantum principles working together. First, the basic electrostatic Coulomb repulsion. Electrons just don't like being near each other. And second, this really weird quantum rule called the Pauli exclusion principle.
The Pauli principle, the one that says two electrons can't be in the same state.
Exactly. It forces the electron's combined wave function to behave in a specific anti-symmetric way. And this mathematical requirement creates this powerful, often subtle link between where the electrons are spatially and how their spins are oriented. It fundamentally connects their movement and their spin direction.
So it's like a quantum mechanical consequence of electrons avoiding each other and obeying the symmetry rule.
Yeah.
And that looks like a force between their spins.
Precisely. It's an emergent phenomena, a quantum effect that acts like a powerful force aligning or anti-aligning spins. It's pretty mind-bending.
Okay, can you give us some concrete examples? How does this exchange interaction actually manifest in real materials? Which ways are most important, maybe?
Sure. There are several key mechanisms, different flavors of this exchange. First, there's direct exchange. This is kind of the simplest idea. Electron wave functions on neighboring magnetic atoms literally overlap in space, but it's very short range, falls off really quickly with distance. So surprisingly, it's often not the dominant player in many of the interesting quantum materials.
Okay, so direct overlap isn't always the main story. What else?
A really crucial one, especially for magnetic insulators, is superexchange. Here you have magnetic atoms, say metal ions, but they're separated by a non-magnetic atom like oxygen. Think of copper oxide materials. The non-magnetic ion in the middle acts like a bridge. It mediates the interaction between the magnetic ions on either side.
So the spins talk through the intermediate atom.
Exactly. And this interaction is very often antiferromagnetic. It favors neighboring spins pointing in opposite directions. And this is super important because superexchange is believed to be absolutely central to the physics of high-temperature superconductivity in the cuprates, which is kind of wild considering it happens in an insulator.
Wow, okay. So superexchange is key for insulators. What other types are there?
Then there's the Dzyaloshinskii-Moriya interaction, or DM interaction for short. This one's a bit different. It's an antisymmetric exchange. It only appears in crystals that lack certain symmetries, specifically what's called an inversion center. And instead of just favoring parallel or anti-parallel alignment, it actually prefers spins to be slightly canted relative to each other. Not quite parallel, not quite anti-parallel, but somewhere in between, often at a 90-degree angle in some ideal cases.
Canted spins. Okay, where does that show up?
It's essential for understanding more complex, non-collinear magnetic structures. For instance, in a material called Q143BDC, which is a Kagome lattice ferromagnet, the DM interaction is responsible for this fascinating pinwheel pattern the spins form. It adds a twist, literally.
Okay, and you mentioned metals earlier. Is there a different mechanism there?
Yes, for metals, where electrons are mobile or itinerant, we often talk about itinerant magnetism, sometimes called kinetic magnetism. Here, the magnetism arises directly from the moving electrons themselves, not just localized spins. A really striking theoretical example is something called Nagaka ferromagnetism. The idea is if you have an electron lattice that's almost full, but you take out just one electron, leaving a hole.
A single hole.
Yeah, just one. That single hole moving through the lattice can actually stabilize a strongly ferromagnetic state, all spins pointing the same way. The reason is kind of subtle. The hole can move much more easily. Its kinetic energy is lower if it travels through spins that are all aligned ferromagnetically. If spins were random or anti-aligned, its path would be sort of blocked more often.
So the hole moves better if the spins cooperate, and that lowers the whole system's energy enough to make everything ferromagnetic, like clearing a traffic jam by coordinating.
That's a great analogy. It's the system lowering its kinetic energy by ordering the spins. It highlights this fundamental difference. Magnetism driven by localized electrons in insulators, like with superexchange, versus magnetism from mobile electrons in metals.
Right, and figuring out which picture localized or itinerant is the right starting point seems crucial for understanding any given material's magnetism. So, okay, we have these exchange forces pushing spins to align or anti-align. But you mentioned exotic states earlier. If the forces just want simple order, what stops them? What creates the really weird magnetic states? The ones that aren't just simple ferromagnets or antiferromagnets?
Ah, yes. That's where things get really interesting. It's usually a powerful combination of three key factors that conspire to disrupt simple magnetic order. First, geometric frustration. This is a fantastic concept. Imagine putting spins on the corners of a triangle, and let's say the interaction is anti-ferromagnetic, so every spin wants to be opposite to its neighbors.
Okay, so spin 1 points up, spin 2 wants to point down.
Right. But what about spin 3? It's neighbors with both spin 1 up and spin 2 down. It can't be anti-aligned with both simultaneously.
Ah, I see. It's stuck. It can't satisfy all the rules at the same time.
Exactly. It's frustrated. This kind of conflict happens on certain lattice geometries like triangles or lattices made of triangles like the Kagome or pyrochlore lattices. This conflict prevents the system from finding a single unique lowest energy state. Instead, you get a massive number of different spin configurations that all have the same minimal energy. It's called classical degeneracy. And this classical confusion, this inability to choose a simple order, is the perfect breeding ground for new, exotic quantum states to emerge.
So the geometry itself prevents simple order. What's the second factor?
Second is low dimensionality. Basically, systems that are confined to one dimension, chains, or 2 dimensions, layers, behave very differently from 3D bulk materials. In 1D and 2D, both thermal fluctuations, just the random jiggling from heat, and, importantly, quantum fluctuations are much, much more powerful. They have a stronger effect in disrupting order. There's even a theorem, the Mermin-Wagner-Hohenberg theorem, which proves that certain types of long-range magnetic order are fundamentally less stable, or even impossible, at finite temperatures in 1D and 2D systems with continuous symmetries.
So being flat or string-like makes it harder to stay ordered, like trying to build a stable house of cards. It's easier in 3D than 2D.
That's a decent analogy. The reduced number of neighbors and the increased influence of fluctuations make order more fragile. And the third key factor is quantum fluctuations themselves. These are different from thermal jiggling. They exist even at absolute zero temperature.
Zero temperature fluctuations.
It's a direct consequence of the Heisenberg uncertainty principle. Quantum systems are never perfectly still. There's an intrinsic wobble or zero-point motion. You can't know both a spin's direction along, say, the x-axis and the z-axis perfectly simultaneously. For spins with a small quantum number, like the spin 12 of an electron, these quantum fluctuations can be incredibly strong. So strong, in fact, that they can completely melt any tendency towards classical magnetic order. Instead of freezing into a static pattern, the system remains in a dynamic, fluctuating, highly correlated state, even at TO0.
Okay, so let me see if I've got this. You take geometric frustration, which creates this massive confusion about where spin should point. You put it in low dimensions where fluctuations are amplified. And then you add strong quantum fluctuations, especially for small spins, which actively fight against freezing. That's the recipe for moving beyond conventional magnetism into this exotic landscape.
That's the essential recipe. Exactly. It's the interplay of those three ingredients, frustration, low dimensionality, and quantum fluctuations, that really opens the door to fundamentally new states of magnetic matter. It's like finding the perfect storm conditions for weirdness.
It sounds incredibly complex to model, though. If you have all these competing interactions and fluctuations, how do physicists even start to study these systems? It seems almost intractable.
You're absolutely right. It is incredibly complex. The full quantum many-body problem is generally impossible to solve exactly. So physicists rely on simplified theoretical models. These are like abstract Hamiltonians, mathematical descriptions of the energy that aim to capture the essential physics of real materials, boiling things down to the most important interactions. And probably the most fundamental starting point for many of these problems is the Hubbard model.
The Hubbard model. Okay, you mentioned it briefly. What does it actually capture? What does it boil down to?
It's remarkably simple in its formulation, which is part of its power. It basically distills electron behavior in a crystal lattice down to just two key parameters. There's a kinetic energy term, usually called T, which represents the ability of an electron to hop from one lattice site to a neighboring one. It describes electron mobility. And then there's an on-site Coulomb repulsion, U. This is simply the energy cost you have to pay if you try to put two electrons, necessarily with opposite spins because of Pauli exclusion, onto the very same lattice site.
So hopping versus staying put because of repulsion.
That's it. That's the core of it, just T and U. But despite this apparent simplicity, the Hubbard model predicts incredibly profound phenomena. One of the most important is the Mott insulator.
Mott insulator, right? You mentioned this earlier.
Yeah.
And it's counterintuitive because normally if you have, say, one electron per site, a half-filled band, you'd expect it to be a metal, right? Electrons should be able to move.
Exactly what standard band theory would tell you. It predicts a metal. But the Hubbard model shows that's not always true. In the regime where the repulsion U is much, much larger than the hopping ties the strong correlation limit, it just becomes too energetically costly for electrons to hop onto a site that's already occupied.
So they get stuck, like a traffic jam on the atomic scale. Even if the road could carry traffic, the cars just refuse to occupy the same space.
That's a perfect analogy. The strong repulsion effectively localizes the electrons on their individual lattice sites. They can't easily move around. And so the system, despite having available states according to band theory, becomes an electrical insulator. This is the Mott insulating state, driven purely by electron interactions, not by band structure effects. And crucially, this Mott state is the parent state, the starting point for many of the most interesting quantum magnets, including the copper oxides, the cuprates that exhibit high-temperature superconductivity when you dope them.
Okay, so the Hubbard model explains how strong repulsion can create an insulator where you might expect a metal. But where does the magnetism come back in? If the charges are stuck, what about the spins?
Good question. So in this Mott insulator limit, the charge degrees of freedom are essentially frozen out because of the large energy cost U to move charges around. There's a charge gap. But the spins of those localized electrons are still there, and they may still interact with each other even if the electrons themselves aren't hopping much. This interaction happens through a kind of virtual quantum process. An electron might briefly hop to a neighbor and back, and this process depends on the relative spin orientations. And when you analyze this process mathematically in the large U limit, what emerges is an effective interaction purely between the spins. This leads directly to the antiferromagnetic Heisenberg model.
So the Hubbard model, in a certain limit, actually becomes the Heisenberg model.
Effectively, yes. The low-energy physics of the Mott insulator is described by the Heisenberg model. The effective spin-spin interaction strength, often called J, the superexchange coupling, is directly related to the original Hubbard parameters. It turns out J is approximately proportional to 4-2 This derivation is a real cornerstone of the field. It provides a solid theoretical justification for why we can often simplify the problem and just focus on spin-only models, like the Heisenberg model, when studying these magnetic insulators.
And the Heisenberg model itself has different versions.
That's right. The basic Heisenberg model treats the interaction isotropically, meaning the coupling is the same for the x, y, and z components of the spin. That's sometimes called the XXX model. But real materials often have anisotropies due to crystal structure or spin-orbit coupling. So we also use variations like the XY model, interaction only in the psi plane, the IZ model, interaction only along the z-axis, or the XXZ model, different coupling in plane versus out of plane. These different models capture different types of magnetic anisotropy.
It's really fascinating how these abstract mathematical models, Hubbard, Heisenberg, Ising, provide this powerful framework, almost like a classification system, for understanding the behavior of actual real-world materials. You can sort of map a material onto one of these models to get at its essential magnetic physics. Okay, so we have the ingredients: spins, interactions, frustrations, fluctuations. We have the theoretical tools, Hubbard, Heisenberg models. What kind of actual magnetic phases these states of matter do we end up with, beyond the ones we learn about in school?
Right. So beyond the familiar phases, first you have ferromagnets. That's your typical fridge magnet. All spins align parallel due to the exchange interaction, creating a macroscopic magnetic moment. This happens through spontaneous symmetry. Breaking the system picks a specific direction to align along, breaking rotational symmetry. Then you have antiferromagnets. Here, neighboring spins align anti-parallel, canceling each other out macroscopically, but forming a regular staggered pattern. The classic example is the nail state, say, in undoped Lau-Iro. This also involves spontaneous symmetry breaking translational or rotational symmetries of the lattice, depending on the pattern. But where it gets really interesting is when we move beyond these conventional ordered states into the realm of quantum disordered phases.
Quantum disordered phases. Okay, what defines those?
These are states where, even at absolute zero, the spins never settle into a static, ordered arrangement. The quantum fluctuations are just too strong, or the frustration is too great. A key example here is the valence bond solid, VBS. In a VBS, the spins don't order magnetically. There's no net moment, no staggered pattern. Instead, neighboring spins pair up to form singlets. A singlet is a quantum state of two spin-12 particles where their total spin is zero. It's inherently non-magnetic.
So they pair up and cancel out their magnetism locally.
Exactly. But the solid part of VBS comes in if these singlet pairs then arrange themselves into a specific static regular pattern across the lattice. For instance, on a square lattice, maybe all the pairs form horizontally but none form vertically. This pattern of bonds breaks a spatial symmetry of the underlying crystal lattice, like 90-degree rotation. So it's solid-like because it breaks the lattice symmetry, but it's magnetically disordered, or liquid-like because there's no magnetic order.
Okay, that's already pretty weird. Solid in structure, but liquid in magnetism. But you mentioned something even more radical: the quantum spin liquid. That just sounds like science fiction.
It really does, doesn't it? The quantum spin liquid, QSL, is probably the most radical departure from our classical intuition about magnetism. It's a highly entangled dynamic liquid of spins that remains disordered, truly disordered, all the way down to absolute zero temperature. It completely defies the usual tendency of matter to freeze into some kind of ordered state as it gets cold.
No order at all, even at T0.
No conventional order. That's the key. Its defining characteristics are really quite something. First, absence of spontaneous symmetry breaking. A true QSL breaks no symmetries. No magnetic order, time reversal symmetry remains intact, and no broken spatial symmetries like in a VBS. All the symmetries of the underlying Hamiltonian and lattice are preserved in the ground state.
Okay, no broken symmetry. What else?
Second, long-range quantum entanglement. This is crucial. The ground state of a QSL isn't just a random soup of spins. It's a highly structured state. But the structure is in the entanglement between spins, extending over long distances. Think back to P.W. Anderson's original idea of the resonating valence bond, RVB state. He envisioned it as a quantum superposition of all possible ways to pair up spins into singlets on the lattice. It's a coherent quantum liquid of these fluctuating entangled pairs. This intricate, non-local pattern of entanglement gives the state a hidden type of order called topological order.
Topological order. You mentioned that earlier. It's not about local patterns, but something more global, more robust, like knots.
Exactly like knots. It's a property of the system's wave function as a whole, not something you can see just by looking at a few neighboring spins. It's robust against local perturbations. You can't destroy it by just fiddling with one small part of the system. Some recent theoretical work even suggests QSLs can exhibit something called disordered hyperuniformity, meaning that even though the spin configurations look random locally, the fluctuations in the density of certain features are suppressed over long distances, indicating a hidden large-scale structure.
It's deeply weird.
Wow. Okay, no symmetry breaking, long-range entanglement, topological order. What's the third characteristic? You mentioned a smoking gun. Right. The smoking gun experimental signature is predicted to be fractionalized excitations. This is perhaps the most mind-bending aspect. In a conventional magnet, like a ferromagnet or antiferromagnet, the elementary excitations are called magnons, or spin waves. These carry an integer amount of spin, typically spin 1. But in a QSL, the fundamental excitation isn't a magnon. Instead, the electron spin effectively breaks apart into new, emergent quasi-particles that carry fractions of the original quantum numbers.
Breaks apart. The electron spin splits. Into what? This sounds impossible.
It sounds impossible from a single particle perspective, but it's a collective emergent phenomenon. The hallmark fractional excitation is the spinyon. A spinyon is a quasi-particle that carries spin 12, like the original electron, but carries no electric charge. In the RVB picture, if you break one of those fluctuating singlet bonds, which has total spin 0, you create two spin 12 excitations, two spinyons, which can then move independently through the spin liquid.
So you create two mobile half spins, but no charge moves.
Exactly. This is the ultimate expression of something called spin charge separation. In one dimension, this is known to happen, but QSLs suggest it can happen in 2D and 3D too. The electron's fundamental quantum numbers, its spin and its charge, become completely decoupled and are carried by different emergent particles. In some theories, particularly related to doped Mott insulators, you might even get Holland's particles carrying charge plus E, but no spin alongside the spinions.
This is really blurring the lines of what we consider fundamental particles. Are there actual materials where physicists think this might be happening, where they might be seeing spinions?
Yes, absolutely. The experimental search for QSLs is one of the hottest frontiers in condensed matter physics. There are several leading candidates, though definitive proof is still debated. A famous one is Herbert-Smithite. It's a mineral containing copper ions arranged on a perfect 2D Kagome lattice, that geometrically frustrated lattice we talked about. Experiments show it has spin 12 moments, strong anti-ferromagnetic interactions, but it refuses to order magnetically down to extremely low temperatures, like 50 millikelvin. And crucially, inelastic neutron scattering sees a broad, diffuse continuum of excitations, not sharp magnons. This continuum is widely interpreted as evidence for mobile, deconfined spinions.
Okay, Herbert-Smithite on the Kagome lattice. Any others?
Another really exciting class are the so-called Kitev materials. These are often honeycomb lattices containing heavy elements like iridium or ruthenium, such as alpha-ruthenium trichloride. These materials are thought to realize at least approximately the Kitev model. This is a very special theoretical model because it's exactly solvable on the honeycomb lattice, and its ground state is rigorously proven to be a QSL. And even more exotically, the fractionalized excitations in the Kitev QSL are predicted to be Majorana fermions, bizarre particles that are their own antiparticles. Finding those would be incredible. There are also candidates for 3D QSLs, like certain pyrochlor oxides, which might realize a quantum spin ice state, a quantum fluctuating version of classical spin ice.
Majorana fermions.
Yeah.
Wow, okay. So if these QSL phases are so radically different from ordered magnets, how does a material transition between them? You said it's not just temperature.
Right. We need to think about quantum phase transitions, QPTs. Unlike conventional phase transitions driven by changing temperature, like ice melting, QPTs occur strictly at absolute zero temperature, T0. They are driven by tuning some non-thermal parameter in the system's Hamiltonian. This could be pressure, applying an external magnetic field, or changing the chemical composition, doping. As you tune this parameter across a critical value, the fundamental quantum ground state of the system changes qualitatively.
So at absolute zero, you crank up a magnetic field, and suddenly the ground state flips from, say, an antiferromagnet to maybe a QSL.
Exactly, or from a QSL to a VBS, or from an ordered state into a quantum paramagnet. There's a whole zoo of possibilities depending on the system. And the point right at the transition, at TO0, and the critical value of the tuning parameter is called the quantum critical point. QCP.
Okay, what's special about that exact point, the QCP?
Yeah. The QCP is where things get really weird and interesting. At the QCP, the system is typically in a scale-invariant critical state. Quantum fluctuations become dominant on all length scales and all time scales. The correlation length and correlation time diverge. Because of this, the system often can't be described by simple, well-defined quasi-particles anymore. It's a highly entangled, fluctuating state that sits right at the boundary between the two phases. You can think of it as a kind of parent state from which the adjacent ordered or disordered phases emerge.
This sounds incredibly theoretical, happening only at absolute zero. Why is this QCP concept so important for real materials, which are always at some finite temperature? Does it matter away from T0?
That's an excellent question, and the answer is a resounding yes. The influence of a T0 QCP isn't just confined to absolute zero. It casts a long shadow, extending its influence up into the finite temperature phase diagram. It creates a wide region above the QCP, often shaped like a fan opening up with increasing temperature, known as the quantum critical region or quantum critical fan.
In quantum critical fan, what happens inside this region?
Systems within this quantum critical fan exhibit highly unconventional physics. They often show strange metallic or non-Fermi liquid behavior. This means the properties don't follow the standard rules we expect for normal metals, Fermi liquid theory. For example, their electrical resistivity might vary linearly with temperature down to very low T instead of the usual T-squared dependence. Their specific heat might behave strangely too. Essentially, the strong quantum fluctuations associated with the nearby QCP prevent the formation of stable, long-lived quasiparticles, leading to this bizarre behavior.
Strange metals. So this quantum critical behavior, driven by a hidden point at absolute zero, could explain some really puzzling experimental observations in correlated electron systems.
Precisely. It's believed to be a key organizing principle, and many people suspect it holds the secret to understanding phenomena like high-temperature superconductivity. For instance, the normal state of the cuprate superconductors, the state above their superconducting transition temperature, exhibits many strange metallic properties. It's widely believed that this anomalous behavior arises because the system is intrinsically close to a QCP lurking at TO, possibly related to the transition out of the antiferromagnetic Mott state. Understanding that QCP might be the key to understanding the superconductivity itself.
Okay, this is getting incredibly deep, but it brings up a practical question. How on earth do scientists actually see these things? These subtle quantum states like QSLs, these fractionalized spinions, this quantum critical behavior. It sounds almost invisible, especially if there's no conventional magnetic order to measure.
You're absolutely right. It's incredibly challenging. QSLs, by definition, don't have a simple order parameter like magnetization. So we need a whole arsenal of sophisticated experimental techniques, often used in combination, to probe their subtle properties. Probably the most powerful and direct probe for looking at spins is neutron scattering.
Neutrons, how do they help?
Well, neutrons are electrically neutral, so they penetrate deep into bulk materials. But crucially, they possess a magnetic moment. They have spin 12 themselves, so they interact directly with the electron spins inside the material. By scattering neutrons off a sample and measuring how their energy and momentum change, you can map out the magnetic structure and, importantly, the magnetic excitation spectrum. This technique is called inelastic neutron scattering, INS.
And what does INS see in these different states?
In a conventional ordered magnet, like an antiferromagnet, INS typically reveals sharp, well-defined peaks in the energy-momentum map. These correspond to collective spin excitations called magnons, or spin waves. You can think of them as ripples propagating through the ordered spin structure. But the hallmark signature of a QSL, particularly one with deconfined spinions, is expected to be very different. Instead of sharp magnon peaks, INS should see a broad, diffuse continuum of scattering extending over a wide range of energy and momentum.
A continuum, like a smear instead of sharp lines.
Exactly. This smear is interpreted as the signature of those fractionalized spinions. Because they are deconfined and can carry any momentum independently within certain bounds, their combined response creates this broad continuum rather than a sharp collective mode. Seeing such a continuum in materials like Herbert-Smithite or Lismozo or even the Kagome ferromagnet Q1-3 BDC, where magnons coexist with the continuum, is considered strong evidence for fractionalization.
Is there anything even more specific neutrons can do?
Yes, there's an advanced technique called polarized neutron scattering. Here, you use neutrons whose spins are all aligned in a specific direction before they hit the sample. By carefully analyzing how the neutron polarization changes after scattering, you can unambiguously separate the purely magnetic scattering from other sources of scattering, like lattice vibrations, phonons, which can sometimes contaminate the signal. This was absolutely crucial, for instance, in studies of the pyrochlore material sigurs, helping to confirm its nature as a quantum spin ice, distinguishing magnetic spin flips scattering from other processes.
Okay, neutrons give a powerful overview. What about zooming in, getting a local perspective right down at the atomic scale?
For that, we turn to local magnetic probes. Two key techniques here are NMR and SR. Nuclear magnetic resonance, NMR, is incredibly sensitive. It uses radio waves to probe the magnetic environment experienced by specific atomic nuclei within the material. These nuclei act like tiny spies, and the magnetic field they feel is directly influenced by the surrounding electron spins through something called hyperfine coupling. A huge advantage of NMR is that it's site-selective. You can often distinguish signals from different crystallographic sites within the material. This is vital for separating intrinsic QSL physics from effects caused by defects or impurities, which are always a concern.
And what kind of information does NMR give about QSLs?
It can tell us about static magnetism, or its absence, through the NMR line shape, and about spin dynamics through measurements of the relaxation rates, how quickly the nuclear spins return to equilibrium. For example, measurements of the relaxation rate can reveal the presence or absence of a spin gap, a minimum energy required to create a magnetic excitation. NMR data suggesting a possible spin gap in Herbert-Smithite was a key piece of early evidence, although its interpretation is still debated.
Okay, NMR uses the nuclei as spies. What about SR? What does that stand for?
Muon spin rotation relaxation, or ANSR, sometimes VSR. This technique uses positive muons, which are fundamental particles, kind of like heavy electrons, but with positive charge and spin 12. You implant these muons into your sample. They thermalize quickly and stop at specific interstitial sites within the crystal lattice. Because they have spin, they act like tiny implanted magnetometers, sensitive to the local magnetic fields around them. The muon is unstable and decays after about 2.2 microseconds, emitting a positron preferentially along its spin direction. By detecting these positrons, you can track how the muon spin precesses or relaxes over time due to the local magnetic field.
So it's like putting tiny compasses inside the material and watching how they wobble.
That's a great way to think about it. And for QSLs, OINSR provides a crucial piece of negative evidence. If there were any static magnetic order, even short-range or glassy freezing, the implanted muons would experience a coherent internal magnetic field, and their spins would precess, leading to oscillations in the measured signal. The complete absence of such oscillations or coherent precession in zero applied magnetic field down to the lowest temperatures is one of the strongest indicators against static magnetism. It tells you the spins are remaining dynamic and disordered, which is a necessary condition for a QSL.
So no oscillation means no freezing, which points towards a dynamic state like a QSL. Makes sense. What about measurements that look at the whole sample, the bulk properties?
Right. Thermodynamic and transport measurements are also essential pieces of the puzzle, giving collective information. Specific heat, measuring how much energy it takes to raise the temperature, is crucial. A conventional magnetic phase transition shows up as a sharp peak in the specific heat at the ordering temperature. The absence of such a peak down to the lowest measurable temperatures is another necessary, though not sufficient, condition for a QSL. It tells you no conventional ordering is happening. Magnetic susceptibility, measuring how strongly the material magnetizes in an applied field, helps determine the strength and nature, ferro or antiferromagnetic, of the interactions. It can also be used to estimate the frustration parameter, basically, the ratio of the interaction strength to the low-temperature magnetic behavior. A large value suggests strong frustration, hinting that the system might avoid simple order.
And you mentioned transport measurements, too, like how heat flows.
Yes, thermal conductivity can be a particularly intriguing probe, especially for potential spin-in contributions. In some layered QSL candidates, the idea is that heat transport within the layers might be carried efficiently by mobile charge-neutral spin-ins. However, heat transport between the layers might be much harder, potentially requiring integer spin excitations or coupling to phonons. If spin-ins are indeed carrying heat in the plane, this could lead to a very large and potentially diverging ratio of in-plane to out-of-plane thermal conductivity as the temperature approaches zero. Seeing such a strong anisotropy would be a unique signature consistent with spin fractionalization.
That's fascinating, using heat flow to detect particles that don't even carry charge. Are there any other, maybe newer techniques people are exploring, pushing the boundaries?
Definitely. The field is always looking for new ways to probe these states. For example, terahertz time domain spectroscopy, TRH-TDS, is emerging as a powerful tool. It measures the optical conductivity at very low frequencies in the THz range. This is interesting because some theories predict that QSLs should host emergent gauge fields, kind of like an internal artificial electromagnetism mediating interactions between the fractionalized excitations. Terahertz spectroscopy might be sensitive to the dynamics of these gauge fields, potentially showing up as a characteristic power law frequency dependence of the conductivity.
Emergent gauge fields. Wow. Any others?
Another direction, mostly theoretical so far but experimentally developing, is tunneling spectroscopy. The idea is to create a junction, maybe by sandwiching a thin layer of the QSL material between two conducting layers, like graphene. Then you measure the current that tunnels across the QSL layer as a function of applied voltage. Theoretically, the features in this tunneling current, specifically its derivative, dIdV, should directly map out the density of states of the QSL's excitations, including potentially sharp features related to spinons or other fractionalized particles. It could provide a very direct snapshot of the excitation spectrum, if it can be realized cleanly.
It's amazing the ingenuity involved in trying to see these almost invisible quantum states.
Yeah.
So if we step back and connect this to the bigger picture in physics, quantum magnetism isn't just some niche curiosity, is it? It seems deeply connected to other huge, unsolved problems.
Absolutely. It's not an isolated field at all. Its study is deeply intertwined with some of the most profound questions. A major one is understanding high-temperature superconductivity. As we discussed, the parent compounds of the cuprate superconductors are 2D antiferromagnetic Mott insulators, prime examples of quantum magnets. Superconductivity only emerges when you introduce charge carriers by doping, which simultaneously suppresses the antiferromagnetic order. What is the relationship? Does magnetism help or hinder superconductivity? P.W. Anderson's famous resonating valence bond, RVB theory, actually proposed that the parent Mott state wasn't just a simple antiferromagnet, but was perhaps already a kind of preformed QSL, a liquid of singlet pairs. In this picture, doping just makes these pre-existing pairs mobile, turning them into the Cooper pairs responsible for superconductivity. While the original RVB theory is still debated, the intimate and complex interplay between quantum magnetism and high-temperature superconductivity remains a central, unsolved mystery.
What about the connection to topological phases of matter? That seems like another huge area where quantum magnetism plays a role.
It's a very deep and fruitful connection. Gapped quantum spin liquids are, in fact, prime examples of systems exhibiting intrinsic topological order. Remember, their order isn't defined by breaking a local symmetry, but by this robust, non-local pattern of entanglement. This topological order is a defining feature of a whole class of new quantum phases. Furthermore, the low-energy effective theories describing many QSLs often turn out to be emergent gauge theories. The fractionalized excitations, like spinons, behave like the electric charges of this internal gauge field. Sometimes there are also magnetic modules of this emergent field called visons. It's like the system generates its own internal version of electromagnetism, and the Kitaev model provides a concrete, solvable example linking a microscopic spin Hamiltonian directly to a topological QSL whose excitations are Majorana fermions, a key ingredient in some proposals for topological quantum computing.
Okay, that brings us to the potential payoff. With all this mind-bending physics, fractionalization, topological order, emergent gauge fields, what are the potential applications? If we could harness these quantum magnetic materials, what could we do? And what are the big hurdles remaining?
The potential applications are truly revolutionary, though still largely futuristic. One area is spintronics. The idea is to move beyond using just the electron's charge, electronics, and also utilize its spin to store and process information. Antiferromagnets, which are a type of quantum magnet, are particularly promising here. They don't produce stray magnetic fields, which helps pack devices densely, and their internal spin dynamics can be incredibly fast, potentially terahertz speeds, much faster than ferromagnets. This could lead to ultra-fast memory and logic devices.
Faster, denser spintronics using antiferromagnets. What else? The quantum computing angle sounds huge.
Indeed. The most exciting, albeit long-term, vision is for topological quantum computing. As we mentioned, the fractionalized excitations in certain topological QSLs, like potentially the Kitaev QSL or others, are predicted to be non-abelian anyons. These aren't just fermions or bosons, they have exotic braiding statistics. If you take two such anyons and physically move them around each other in a specific path, like braiding threads, the final quantum state of the system depends not just on the final positions, but on the order in which you perform the swaps. This non-trivial transformation upon braiding can be used to perform quantum logic gates. And the beauty is that the quantum information is stored non-locally in the topological state, making it intrinsically protected against local noise and decoherence, the biggest enemy of current quantum computers. Building a fault-tolerant quantum computer is the holy grail, and topological QSLs offer one potential pathway.
Intrinsically fault-tolerant quantum computing based on braiding particles in a spin liquid. That's incredible potential. But it sounds incredibly difficult to achieve. What are the major roadblocks still standing in the way?
Oh, absolutely. The challenges are immense. Several significant ones remain. First, material synthesis. Finding and creating materials that actually realize these delicate QSL ground states is incredibly hard. We need extremely pure single crystals, often large ones, to perform sensitive measurements. Even tiny amounts of disorder, defects, or impurities can easily mask the subtle QSL physics or induce conventional ordering instead. It's a constant struggle for material scientists.
So just getting the right stuff is hard. What else?
Second, definitive experimental proof. As we discussed, we have many promising candidates and compelling evidence from various techniques, thermodynamics, neutrons, NMR, SSR, but a truly unambiguous smoking gun experimental signature, something that absolutely proves the existence of, say, fractional quantum number or demonstrates non-billion braiding statistics is still missing. It's the focus of intense worldwide research efforts.
The smoking gun remains elusive. What about theory?
Third, theoretical and computational complexity. The quantum many-body problem underpinning these systems is fundamentally hard. Even simulating the ground states and dynamics of relatively simple models like the Hubbard or Heisenberg models on 2D or 3D lattices pushes the limits of our most powerful supercomputers and numerical techniques, like DMRG, QMC, tensor networks. Each method has its own biases and limitations, making definitive theoretical conclusions challenging.
And the defining feature itself.
Exactly. Fourth, characterizing entanglement. The very property that defines these exotic states, long-range, multipartite quantum entanglement, is notoriously difficult to quantify and measure directly, both theoretically and especially experimentally. We need better tools and protocols to probe the intricate entanglement structure that distinguishes a QSL from a trivial disordered state. It's the heart of the mystery, but also the hardest aspect to get a direct handle on.
Wow. So we've really journeyed today. From the simple fact that classical physics can't even explain a basic magnet, we've plunged into the quantum world of electron spin, exchange interactions, frustration, and ended up in this incredible landscape of quantum disordered phases, valence bond solids, and the truly mind-bending quantum spin liquid states defined by entanglement and hosting fractional particles that might one day power fault-tolerant quantum computers. It's a field that genuinely pushes the absolute boundaries of our understanding of matter. And for you, our listener, here's a final thought to perhaps mull over. Think about that quantum spin liquid. It appears disordered, maybe even empty in terms of conventional magnetic patterns. Yet we've learned it's actually brimming with complex, dynamic, hidden structure, this intricate web of quantum entanglement that might hold immense potential. It makes you wonder, what other hidden orders, what other complex information might exist in systems around us that just look disordered or chaotic on the surface, waiting for us to take a deeper dive and figure them out?